Hello and welcome to the first of the lectures in this week 7 of the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In the last week of lectures, we were introduced to the basic schema of a fuzzy inference system, and we went on to see one major type of fuzzy inference mechanisms or fuzzy inference system, which is that of fuzzy relational inference. We looked at how to perform the inference in the presence of a single rule, be it single input, single output, or multi-input, single output, and also in the case of multiple rules, where we brought in two different types of inference strategies, that of first infer then aggregate and first aggregate then infer. In this week, we will look at the second major type of fuzzy inference systems, that of similarity-based reasoning. In the first lecture of this week, we will have a gentle introduction to fuzzy inference systems, specifically one type of similarity-based reasoning. We will largely go with a visual illustration of the entire inference process itself. But before that, if you were to trace back in history and look at who could be considered as the fatherly figures of fuzzy set theory, definitely Professor Lotfi Zadeh, without any hesitation, can be attributed to bringing in fuzzy set and its applications into the stream of engineering. He was a professor of control theory in UC Berkeley, and with a seminal paper in 1965, he showed that fuzzy sets can be brought into use in engineering streams. As a control engineer, he brought them into use into control systems. In one of his prefaces to a book, he had divided fuzzy logic, or what he called fuzzy set theory as fuzzy logic, into two major types or broad divisions, that of fuzzy logic in the broad sense and fuzzy logic in the narrow sense. Fuzzy logic in the broad sense, he said, refers to all the engineering applications where fuzzy set theory is being used. And according to him, fuzzy logic in the narrow sense can be thought of as the logical aspects, the algebraic and analytic aspects of fuzzy set theory itself. And if one were to trace back in history as to who could be considered as the fatherly figure for this, almost unarguably, it has to be Jan Łukasiewicz, who during the early 20s proposed multivariate logic and discussed and explored them. So these perhaps are the two fatherly figures for fuzzy set theory, looked at in the sense of theoretical or explorations or in applicational aspects. But with this short introduction, let's get into fuzzy inference systems. We have seen fuzzy relational inference, but we will look at one particular type of similarity-based reasoning visually. Before that, we should also understand where fuzzy inference systems themselves are being utilized. We know why the need for fuzzy set theories itself arose, but now we are discussing where are we using fuzzy inference systems. As was mentioned, Professor Zadeh himself was a control systems engineer, which meant initially it was applied in control systems. These days you hear about fuzzy logic washing machines, fuzzy logic camcorders, and what have you. But perhaps one of the earliest systems to adopt using fuzzy set theory was the subway system in some of the cities in Japan, especially that of Sendai. Next came decision making, quite obviously and naturally, because we are dealing with reasoning, and fuzzy set theory still plays a major role here in the form of being incorporated into expert systems, multi-criteria decision making, ranking of alternatives, and so on. And of course, when you look at it from the point of view of data analysis, we know that fuzzy set theory, fuzzy inference systems form part of what they call the soft computing. So they play a huge role in data analysis, specifically in the areas of image processing, in terms of image segmentation, edge detection, and also in classification. Having said this, we said that as a control engineer, Professor Zade brought fuzzy set theory into control systems. And at that time, he had explained his motivation for bringing in fuzzy set theory. Of course, a control engineer would be able to better present it and better understand it. But only so that we have an idea of what used to happen with classical rule-based systems and how fuzzy set theory helps us in an immediate sense. Let's look at a watered down version of a classical rule-based system and identify some kinks which we can immediately iron out by the introduction of fuzzy sets. So in classical rule-based control, we want to control a system and have a control system there. What does a control system do? It controls the output of a system. So given an input, it controls the output based on the input. So in that sense, it is a mapping between inputs and outputs. Quite clearly for us now, this relation between input and output is given in the form of if-then rules. Classical if-then rules. Let's look at an example. So let's say that we want to implement a control system for an air conditioner. Now, what could be the goal of an air conditioner? Ideally, it is to keep the room temperature at a constant. So now, to help us do this, what are the components present in an air conditioner? The working of it could be captured in just these 2 points. So you have a thermostat which senses the room temperature and accordingly adjusts the fan speed, essentially the RPM of the motor, rotations per minute of the motor. So the inputs here are the varying room temperatures which the thermostat senses using some sensors, and the output is the speed of the motor, the fan speed, which it adjusts. So essentially, by measuring the temperature, we need to handle or assign an appropriate fan speed for the motor. How would we do this? So if we were to capture it, there is a function behind the working of the system. So if T denotes temperature and S denotes the fan speed, then there's a function mapping between T and S. So you could say S is equal to F of T. This function, obviously we do not know, or even if we know, we need to be able to simulate it. We need to be able to approximate using the control system. But what we do know qualitatively is they have a monotonic relationship. As T increases, we want S also to increase. So perhaps we could come up with rules of this type. If T is between 20 and 30 degrees, then the fan speed should be 300 RPM. Similarly, if T is between 30 and 40 degrees, then the fan speed should be 700 RPM, and if it is more than 40, then the fan speed should be 1000 RPM. So there are a few things that perhaps we should note here. Firstly, if you look at these rules, these are classical if-then rules, because you have, if you recall what we have done in one of the earlier lectures in the last week, we started with a classical if-then rule where it is of the form, if X belongs to A, then Y belongs to B. You could look at T belonging to 20 to 30 degrees as T belonging to the interval 20 to 30, which is essentially a subset of the domain, whatever we are considering as the temperature domain. And S is equal to 300 RPM, so you could look at 300 RPM as a singleton set. So it is more like if T belongs to A1, then S belongs to B1. Of course, in this case, B1 is just a singleton set. So we are looking at really classical if-then rule. Second thing that we should note here is, given a T, how does it work? All it does is it checks, much like a couple of lines of code that you would probably write in a basic programming language like C. If T is between these two values, then S should be this, assign S this value. And you will see that there is no overlapping here, so you would just use if, else if, else if. So that kind of a structure you have here, and that's how the inference has been done. So the inferencing with classical if-then rules is very clear, straightforward. And there is no parallelism because we do not allow for overlapping sets. So only one of these rules comes into play for a given temperature. Now, some immediate limitations can be pointed out. The first of them is this. Look at it, the change in temperature because that's what finally we are controlling using this control system and air conditioner. And that's what we feel also when we keep the air conditioner on. The change is sudden and not a gradual one. Why do we say this? Let's say at time t1 the temperature is 37 degrees and according to the rule the fan speed should be 700 rpm. So after a certain time period it starts to cool down and the temperature drops to 30 degrees. The moment it drops to 30 degrees at time t2, the second rule kicks in and it says that no, we should run it at 300 rpm. That's the first rule there, what we saw in the earlier slide. But what is interesting now is, consider the time t2 minus epsilon for some small epsilon. At that point of time, the fan speed was running at 700 and now suddenly you have shifted from 700 to 300. It is not a slow gradual change. And hence, accordingly, the temperature variation also will be sudden and not gradual. Not only is the temperature variation not gradual, this also leads to excessive wear and tear of the mechanical parts. So not only are you not having a very nice comfortable feeling inside the room with air conditioner on, but in the long run it probably is detrimental also to the functioning parts inside the AC. So these are some simple limitations that you could show with classical rule-based control. But let's see how we could manage this by introducing fuzzy sets here. Let's look at fuzzy rule-based control. Obviously, fuzzy sets form the building blocks of fuzzy if-then rules. We have seen this. If the air temperature is cool, then set the motor speed to slow. This is one type of fuzzy if-then rule. A typical general schema would be if X is A, then Y is B. In this case, cool is A and slow is B. These are the fuzzy sets. Well, what is a fuzzy inference system? We know this. It consists of two things. First, a set of fuzzy if-then rules, so a rule base, and an inference engine. So one type of inference engine is what we have seen in the last week of lectures, that of fuzzy relational inference. The behavior of a system can be indicated by a function f, because we are giving an input and expecting an output. Now we are in the setting of control systems. What does a fuzzy inference system do? It does function approximation. It tries to approximate the behavior of a system, simulate the behavior of the system. We have a perfect idea of what that system, how that system should function. Given this temperature, what should be the fan speed? And it is trying to approximate it. Of course, often we do not know this function f. We are only trying to approximate this even without knowing it. And FIS, fuzzy inference system, covers the graph of f with rule patches. The last 2 points are extremely important and we will keep coming back to this throughout this lecture. Firstly, a fuzzy inference system does function approximation. How does it do it? It does it by patching up the function itself, the unknown function itself, in terms of rule patches. As we go along, this will become clear to all of us. Okay. So now, generally what do we have? We are given an input and we want an output. How do we do this? We are given some ground truth, because we cannot arbitrarily assign output. So the ground truth, the knowledge about the domain, is given in terms of a set of if-then rules, the fuzzy if-then rule base. Now we want to use this rule base and intelligently reason some output for this given input. And that is where inference engine comes into picture, the knowledge and the intelligence. So this input is given to the inference engine and we are expecting an output. Remember, what we have seen earlier was we are actually giving a fuzzy set as an input to the inference system. Whereas now we are talking about control system and we are actually talking about temperature. And when we are sensing the temperature, that the sensor senses will not be a fuzzy set. It will probably say 32.3 degrees or 37 degrees. So often inputs are either real numbers or real vectors, and there is a need to fuzzify them. We will see these in detail, but in this general schema, let's also have this component. So typically, if the input is not a fuzzy set, it is fuzzified and given to an inference engine. What does the inference engine do? It talks to the rule base, takes the help of the rule base and gives us an output. Either an output in the form of a real value or real vector, or perhaps just a fuzzy set, like in the case of fuzzy relational inference we have seen, we get B dash, which is finally defuzzified into obtaining an output. We will see all of these components in play presently. So this is the overall scheme of any fuzzy inference system. These are the components that you would have. Okay. So let's stay with this example of building a fuzzy controller for an air conditioner. So we have identified that input is the air temperature, output is the motor speed, and motor speed is what we want to control. By controlling the motor speed, we want to control the air temperature in the room. So we would come up with some rules. Let's say that these are the rules that we have come up with. If X is cold, then Y is stop. So fan need not rotate. If F is cool, maybe it has to operate slowly just to circulate the air. And the rest of the three rules that we have here are quite commonsensical. If it is medium, average speed, hot, fast speed, very hot, blast speed. So these are the 5 rules that we have in this system for the moment. Now, we saw that fuzzy sets form the building blocks. So once again, if you are talking about these fuzzy sets, cool, fast, average, medium, then we need a domain on which it could be defined. So we need an appropriate domain and we need an appropriate way of defining it also. So if instead of fuzzy set, if you had gone for a classical sets, we would have some interval like this. So t falling within that interval is what a classical if then rule would capture. But in the case of now we are discussing fuzzy if then rule, so then we are using fuzzy set, and we know that given any value which falls in the support of this fuzzy set, we can find its membership value. In this case it's 0.6. So what is the first step? So we want to control this. We have come up with the rules. These rules we know capture the working of the system. We still do not know exactly what is that function f which maps x to y, but we more or less have an idea of how the system should function, and that's what we have actually expressed in the form of linguistic rules. First step is to partition the input space. Come up with a fuzzy partition of the input space. What do you mean by that? We understand fuzzy partition, or more general sense, a fuzzy cover is a collection of fuzzy sets whose support will cover the entire domain. That's all that is expected of a fuzzy cover. So now here the input space is the temperature domain. Let's for the moment assume that it varies from 10 to 30 or a little more. Now on this we need to define how cold looks like, how cool looks like, how medium looks like, and so on and so forth. So perhaps let's assume that for us presently cold is this kind of a triangular fuzzy set. That means at 10 it is definitely cold, but at 13 it is not really that cold, maybe cold only to the extent of 0.5. The next concept is that of cool. Now you see here, cool, perhaps 12 is not cool, but from 12 to 20 everybody is cool, but to a certain degree. And immediately you see that we are actually overlapping cold and cool. That means the point here, maybe it is 13.5, it's both cold and cool. This could not have happened in the classical if then rules, because we actually have non-overlapping sets. That's how we do the partition there using those classical sets. We will look at a set of rules, their completeness, past rule basis in perhaps the next lecture. So for the moment we are trying to capture these concepts, cold, cool, hot, very hot, in terms of fuzzy sets on the chosen domain of x, which is the temperature domain. So let's assume that medium looks like this, hot like this, and very hot like this. So these are the 5 fuzzy sets that we have defined on the input domain x. Next, the logical step is to partition the output space. The output space is y, which consists of motor speed. Let's assume that these are the motor speeds that we have in terms of RPM. And for the moment, let's have only 3 output fuzzy sets. Fast, which should of course look like this, somewhere on the right extreme. Slow, which is on the left extreme, and average. So let's assume that these are the only 3 fuzzy sets we are going to have on the output domain. Recall, in the last lecture of previous week, when we were talking about inferencing using FRI, fuzzy relational inference, in the presence of multiple rules, a rule base, we had said that often it is the case that the number of fuzzy sets, linguistic values on X, the input domain, typically are far more than the number of fuzzy sets or linguistic values that you can have on, you want to have on the output space Y. And this is one such clear example where we have this 5 input fuzzy sets but only 3 output fuzzy sets, or 5 antecedents and 3 consequents. Okay, so now let's look at these rules. So now we understand everything here. What is code, what is stop, what is cool, what is slow, so on and so forth. Now, the inferencing itself. Remember, what we said was a fuzzy inference system approximates a function. What is that function? It captures the working of the system. So there is some particular way in which an air conditioning control system should work. That's what we feel. If this is the temperature, this should be the speed at which it should cool. If this is the temperature. So we have this mapping in mind. We have it only in mind. We do not know exactly. If it were known, then we could easily code it. So we want to capture that unknown function more or less using a fuzzy inference system. So we have the system does operate according to a function f, which perhaps we do not know, which is a function from x to y. And let's say it looks like this. Look at this. We are not taking a linear function, just only increasing. It's non-linear, but a kind of a nice smooth kind of a step function. So at every point it increases smoothly and stays for longer and then slowly starts to increase. This is the kind of function perhaps we feel is ideally suited to control an air conditioner. Now how are we going to manage an FIS approximate this function? So on the x-axis you see the temperature domain, and the y-axis you see the fan speed domain. So now what have we done? We actually have a fuzzy partition on x and a fuzzy partition on y. Now how do the rules look like? The first rule that we have is the second rule. If x is cool, then y is slow. Now look at the set cool. Who are the people who belong to this set cool? So essentially you are looking at the support of this fuzzy set cool, which is the support. It is between these two values, because outside of it, it is 0. So that means only those x's, when you are actually measuring the input x, only if it falls within this interval is it going to be considered as cool. And only then this rule needs to come into picture, because we are in that if region. Now, what about slow? Who are all the values who would get some non-zero membership value in the fuzzy set slow? So you will see that these are the y values coming from the domain of y, domain of fan speed, which will actually belong to slow. The support of slow is this. Now if you look at this entire region, how can we interpret this? So this region consists of all those ordered pairs, x comma y or u comma v, such that u belongs to cool to non-zero extent and v belongs to slow to a non-zero extent. That's one way to see it as positive example. Another way is if x is cool, then y is slow. So you're insisting if an x falls here, excites cool, that means belongs to cool, then you are insisting that the y somehow should belong to slow. That's what you are insisting as a restriction, as a constraint. Now this is what a rule does. So we said an FIS covers the function with rule patches. So you see this rule, it is actually patching up part of the domain. Let's continue further. Look at this rule. If x is medium, then y is average. What part of the domain would it cover? Clearly this, where on the x-axis you have taken the support of medium, on the y-axis you have taken the average or support of average, and essentially you are doing a Cartesian product. So then every rule you actually take this depending on the supports. So now you see here what we have is this. We said an FIS covers the graph of f with rule patches, and how are we covering? We are essentially taking the Cartesian product of the corresponding supports, and you see that these patches are in fact capturing the function. The function continues to remain within these patches. Clearly, if you have more fuzzy sets on both the domain and the range, the codomain, then these patches will start to shrink, which means you're going to have smaller and smaller patches approximating these functions. Which is preferable? Perhaps will be clear in a few slides that we are going to see now. So the key takeaway from this graph is an FAS covers the graph of F with rule patches. That should be more in mind. Okay. Now let's look at how the inference itself is done. Inference is done in a parallel manner. Now if you think back at fuzzy relational inference, there again it was parallel in the sense that we were aggregating and doing it. So in the case of theta, clearly it was parallel because A dash was given to each one of those rules. They were excited and they were giving us B1 dash, B2 dash, so on till Bn dash. And finally we aggregated them to get a single B dash. So here again, the inference is parallel, of course, because it is a fuzzy inference system. What do we have? We have this partition on the input domain. Let's assume 18 is the value that is given to us as input. That means the sensor in the air conditioner sensed it is 18 degrees centigrade. The question is, what should be the fan speed? That's what we want to do. How do we do this? First, we check to what extent 18 belongs to different fuzzy sets. It is clear it belongs only to the fuzzy sets cool and medium. And to what extent? We'll find out presently. So among these 5 rules, since the given input is 18 and it belongs only to cool and medium, these are the only 2 rules that can come into play. Of course, we know that we have a lot of knowledge, but what is useful or important, appropriate, relevant for the problem at hand, that's what we are going to pick up. So given that the input is 18 degrees, so these are the 2 rules that come into play because 18 belongs to only both cool and medium. Now the inference itself. So it is sufficient to consider these 2 fuzzy sets, cool and medium on the X domain and slow and average on the Y domain. Now we are given 18 degrees. Now let's look at to what extent 18 belongs to both of these fuzzy sets. To medium, it belongs to degree 0.2, and to cool it belongs to degree 0.2, and to medium it belongs to degree 0.7. Now what do? We take this. Remember, cool is related to slow and medium to average. We take this value, the extent to which 18 degrees is captured by the concept cool. We take that value. Essentially, we will see in the next lecture that it is called the similarity value. It tells you to what extent 18 belongs to cool. We are taking this value and we are modifying the corresponding consequent, which is the slope. How are we modifying? Perhaps we will just cut it off, we'll threshold it. If you are looking at min kind of an operation, we'll just threshold it. So you see here, using the extent to which a given input belongs to the antecedent of a rule, to that extent we are modifying the consequent. And in this case, when we talk about modifying, we are just only thresholding it. So similarly, the consequent for medium is average, and 18 belongs to degree 0.7 in medium. So we will take this value of 0.7 and accordingly we'll threshold the average fuzzy set. So now, given an input, it has excited 2 rules and you have 2 fuzzy sets as output. But what we need finally is one value which can be told to the motor and said, okay, run at this speed. That's what we want to do. How do we do this? First, we take the union of sets. Remember, union means we are aggregating this. So you might think that it is already trying to look like B1 dash and B2 dash and we are aggregating it. If you think like that, we are not very far away from the truth. We will see this in a few lectures from now. So this is the union of sets. Or the local outputs are the modified slow and average, and now we have aggregated into a global fuzzy set. From this, we need a value. How do we do this? This is where the defuzzifier comes into picture. Now this is a fuzzy set. We want to go from a fuzzy set to a value, typically within the support of this fuzzy set. So we apply a defuzzification or defuzzifier. Let's assume that we are applying the centroid defuzzifier here. And what do we get? The centroid of this entire fuzzy set is here, perhaps, and it says it is 680. So that means for 18 degree input, we are actually getting 680. Now you see that it is neither 700 nor 300. So now as temperature goes below, it is probably going to go towards 300 more, and as temperature rises above, it will not be cool or medium, it will go to the fuzzy sets further in the extreme right. So maybe it is hot or very hot, and accordingly instead of slow or average it will be fast, which means again the motor speed is going to move to the right of your screen, and which means it's increasing the motor speed. So you see that we have nicely captured this monotonicity relationship using these partitions. Once again, quick recap. What is a fuzzy inference system? It consists of two things: the knowledge base in the form of fuzzy if-then rules, and the intelligence in the form of an inference engine. We are trying to capture the behavior of a system, which we assume is a function f mapping x to y. A fuzzy system does function approximation. It just only tries to approximate this system behavior. Most importantly, it does this by covering up the function. We don't know the real function, but we are covering it up with patches wherever we think the function could fall using the corresponding rules. So far, we have seen how fuzzy if-then rules are being used. Fuzzy rule-based inference system. We have seen this in the last week of lectures too. In this lecture, we have seen the need and working of an FIS. It is very different from fuzzy relational inference that you would have noticed already. We are going towards similarity-based reasoning. We will relate it to it. Already we have used some terms which you are familiar with: aggregation, modification, and so on. What's left? Let's quickly have a look at the different types of fuzzy inference systems which are based on similarity-based reasoning, some properties and issues, some desirable properties and some issues that we would face. What are the types of SBRFIs? To understand that, we have to look at two practitioners who have come up with these models. The first of them is Abraham Mamdani. During these mid-70s, he had come up with a few papers dealing how you could do similarity-based reasoning. Now what we understand as similarity-based reasoning, he had proposed his form of fuzzy inference, which is now called the Mamdani inference system or Mamdani form of fuzzy inference system. A little later, Professor Michio Sugeno, he proposed an alternate way of doing similarity-based reasoning called the Tagaki-Sugeno fuzzy system. It is also called the Tagaki-Sugeno-Kang fuzzy system, or abbreviated as TSK fuzzy system. These are the two pioneers who proposed these major and to this day very useful models of similarity-based reasoning fuzzy inference systems. What are they? So if you look at fuzzy inference system, as was repeated many times, there are two major types. First is the similarity-based reasoning. Other is the fuzzy relational inference, which you have seen in the last week of lectures. And the similarity-based reasoning, there are two important reasoning schemes, fuzzy inference systems, that are proposed by Mamdani and the one proposed by Tagaki, Sugeno, and Kang. These are two things that we will see going forward in the next week of lectures. What are the desirable properties? Just like in the case of fuzzy implication, we said that these are the desirable properties: IP, identity principle, ordering property, exchange principle. In the case of fuzzy inference systems, what do we expect? Well, we'll expect that it interpolates. The inference is interpolative. What do we mean by interpolative? We'll define this soon enough. Essentially, you're looking at how is the rule base constructed, based sometimes also from data that are coming out of the system. So now, the way you have constructed the rule base and used the inference system, you're asking the question, if I give the input from the data, I already have input-output pairs from the data which I have measured. If I give this input measurement, will it get the corresponding output measurement? So that's essentially the interpolativity. Continuity of inference. So what I get, the input-output mapping, is that function finally continuous? Continuous in the sense that we understand over the real or in the appropriate domain. Universal approximation. So we said that fuzzy inference systems do function approximation. So the question now is, can we approximate any continuous function? We assumed in this case of an air conditioner a smooth, nice looking monotonic curve. But what if it were oscillating oddly or wildly? Will we be able to approximate that? This is a question that we need to answer. Monotonicity of inference. If there is an ordering between inputs, will the same ordering be maintained on the outputs also? For example, for 18 degrees, I get 680 as the RPM. When I go to 20, it should actually go higher than RPM, because higher than 680, because it has got hotter. Suddenly, if it falls down, if it says no, run it at 650, then there's something wrong with it. And finally, robustness of an inference. This is slightly different from continuity. We'll explain this in the context when we take this up in the coming weeks. So these are some of the desirable properties of a fuzzy inference system. And what are some issues? Well, one of them we have seen, dealing with the meso and fuzzy relational inference, the computational complexity, both storage and the calculation or computing complexity. And in the scenario of control systems, stability is also extremely important. So instead of starting from one point, if you start from another point, would the system still be stable? That's what is the question here. We will not go into this because we are not going to talk about control systems so much, but we'll definitely deal with computational complexity and also this combinatorial rule explosion. That means you have unwieldy number of rules. So one is computational complexity, and this leads to both computational complexity and also storage complexity. So the first and last ones we definitely will look into during these lectures. Well, a quick recap of what we have discussed in this lecture so far. We looked at a particular type of similarity based reasoning only visually. We will look into the operations in the next lecture. We know that each of the if-then rules captures knowledge of some part of the domain. We have seen that. We know that an FIS does function approximation, and it does that by covering the function through rule patches. We will keep referring to this, and this idea will also allow us to present many perspectives on the inference system itself, and especially about the fuzzy if-then rules. What's coming up? We will discuss the operations involved in similarity based reasoning, give it a general and formal framework, just as how we did for fuzzy relational inference. Interestingly, you will look at if-then rules as what are called fuzzy points, pairs of fuzzy points. And once you see it like this, you could look at FIS, fuzzy inference system, itself as an interpolation of these fuzzy points. And of course, we look at Mamdani and TSK fuzzy systems in little depth. Finally, we will like to simulate these things on MATLAB. So what we mean by simulation? So we know that fuzzy inference system approximates a function. So we assume that we take a function, assume that it represents the working of a particular system, and we see how to build a fuzzy inference system which approximates that, which essentially means finding a proper corresponding. Once the function is given, the domain and range are known, then it's about partitioning the domain and relating them nicely, relating these fuzzy sets nicely so that you could form rules which make sense in the context, and then choosing the operations, the operators, and performing the inference. Some references, more than calling them references, these are my favorite resources, especially in this topic on fuzzy inference system. The book by C.T. Lin and George Lee, also the book by Pasino and Irkovich. These are very, very good references. They explain things in a much simpler way, good textbook material, and they have a lot of topics covered too, and also the book of Angel Piaget. As I said, in the next lecture, we will look at putting similarity based reasoning in a formal framework, what are the operations involved, and also a little bit about types of fuzzy rule bases, sparse, complete, and so on. Glad you could join us for this lecture, and hope to see you soon in the next lecture. Thank you again.